Hey, so today we're going to be continuing on looking at magnetism and the effect that it has on charges. Uh, we've been looking at, we just finished up talking about how a moving charge, in a wire, creates a magnetic field around the wire. We talked about the right hand rule. If I put my thumb in the direction of the current and kind of curl my fingers around the finger direction tells me the direction of the magnetic field around the wire. Now we're going to look at the kind of flip of that. So that was a charge kind of creating a magnetic field, having an effect on a magnetic field. Today we're going to look at what effect does a magnetic field have on a moving charge. Uh, we're going to hold off talking about directions for the most part, but really all we need to know is that the force of the magnetic force, if you will, the force from the magnetic field is equal to uh, the absolute value of the charge, whatever it is, whether it's a proton, electron, positive or negative, doesn't matter. We're just taking the absolute value. We're just treating it like it's positive, times the velocity of that charge. So keep in mind, if the charge is not moving, we're not going to see this happen. So times the velocity, times the electric field strength, depending upon how far we are from the magnetic field or with the problems we're going to be working with, it'll be a uniform electric field. um, times the sine of the angle relative to that magnetic field. Okay. For the most part, what that means is if my charge, so let's say that I got my current carrying a wire here, and we're going to say that I is going this way, and it's in a uniform magnetic field, and this time we're just going to say that the magnetic field is just kind of coming out of the page there. I'm not going to do all of them. Really what we're going to see is that since this current is perpendicular to the magnetic field kind of coming out of the page, it's going to get deflected. It's going to experience a force uh, perpendicular. We'll go through the directioning stuff next time, but really what we're seeing is that the force is going to be perpendicular to the current and the magnetic field, uh, or I should say it's really perpendicular to the magnetic field. That's really the relative part that we're going to be looking at there. All right, so let me get rid of that stuff quick. So let's look at what that kind of tells us here. So we've got two objects. We've got object one with a charge of 3.6 microcoulombs and a speed of 862 meters per second. All right, so that thing's booking. It's traveling at right angles to a uniform magnetic field. And then the magnetic force it's going to experience, let's just call that force 1, is 4.25 times 10 to the negative third newtons. Okay. Object 2 with a charge of 53 microcoulombs, so a lot more than charge 1, but with a speed of 1.3, 1,300 or 1.3 times 10 to the third meters per second. So it's moving, quite a bit faster. Moves at an angle of 55 degrees relative to the same magnetic field. Find A, the strength of the magnetic field, and B, the magnitude of the magnetic force exerted on object 2. All right, so as you notice, I kind of quit writing stuff down. I didn't even touch object 2 with what I wrote down. Because essentially, if I'm looking at this equation here, I have Q, I have velocity, I have the force, and they tell me it's perpendicular, so that means it's 90 degrees. The charge is moving 90 degrees compared to the magnetic field. I can even map that out. So if I'm saying that let's say that the charge is going that way, and my magnetic field, I'm just going to use an arrow. If that's my B, the charge is moving perpendicular to it. Um, they're perpendicular to each other. So really, and if I take the sine of 90, you can plug that in real quick. It's just 1 multiplying by 1 doesn't change anything. I don't even care about that. All right. But the thing I'm missing from this equation from just object one is this B, the magnetic field. And that's going to be the magnetic field for both of them. In fact, if I look at object two, the charge of object two we said was 53 microcoulombs. It had a speed of, I'm just going to say 1,300 meters per second. Its angle, though, is 55 degrees. And they want to know, part B of the question is what's the magnitude of the magnetic force exerted on it. All right. But in order to find, so they give me Q, they give me V, they give me theta. They want to know F before I can do that. I actually have to know B first, and let's even like do a quick diagram there. So let's say my magnetic field is still going this way. I'm going to draw kind of my x-axis there. But this charge, what they're saying is going, let's go this way. So if that's my Q, Q2, they're saying that it's moving 55 degrees from it. Okay, just to kind of diagram it out a little bit more. All right, so but before I can do part B, I have to do part A, and I'm going to look at object 1 to figure out part A. So sine of 90 part I don't need to care about here. So if I need to get B by itself, though, and this is pretty easy. If I want to get B by itself algebraically, it's being multiplied by Q and V. So to get Q and V over to the other side, I'm going to just divide by that on both sides. So I've got force over the absolute value of Q times V. All right. In this case, the force we said was 4.25 times 10 to the negative third newtons. I'll pop that in parentheses just because it's scientific notation. And I'm doing multiplication and division over the absolute value of Q. We didn't care, that it's a positive or negative. I do have to convert this to Coulomb, so I've got 3.6 times 10 the negative 6 coulombs times the velocity, so times 862 meters per second. Send that out a little bit more. Get out the calculator here. Uncover the math I need to do. All right, so I've got 4.25 times 10 raised to the negative third power divided by, let's go parentheses, parentheses, 3.6 times 10 raised to the negative 6 coulombs times 862. Close out the parentheses in the denominator, hit the equal sign. And it looks like my answer is going to be 1.37. I could probably call that 1.4. I'm going to leave it 1.37 for now. I don't care too much about sig figs for the most part. So I've got 1.37. Magnetic field strength is still in Teslas. Okay, so that's the answer to part A. Okay, that's the magnetic field. So I can come over here and I can even pop that number over here in the B part. Nope, got too far. Got a little bit distracted there. Oh. All right, make that a T. All right. So now I've got enough stuff where I can actually figure out the force for part B here. I don't need to do any algebraic rearrangement here. I'm going to say that force for part B is going to be equal to Q, 53 microcoulombs. Let's go ahead and rewrite that as 53 times 10 to the negative 6 normal coulombs times the velocity, 1,300 meters per second, times the strength of the magnetic field we found to be 1.37 Teslas. And we got to take that times the sine of 55 degrees. All right, so I'm going to have to do a little bit of trig here. Once again, calculator out. This time I'm going to move it to the other side. I'm actually going to, because of how this calculator works, I'm going to start with the sine of 55. So I'm going to go 55 sine, and then I'm going to go times, parentheses, 5 point, nope, not point, but just 53 times 10 raised to the negative 6. Close parentheses, just make sure my PEMDAS is right, times 1,300 meters per second times 1.37 Teslas. I already took care of the sine part at the beginning. Go ahead and hit equals. We got 0.077. I think that sounds fine. 0.077. Newtons, or if I want to be able to compare the two forces, if I want to write this in scientific notation, that'd be 1, 2. So I've got 7.7 times 10 to negative 2 newtons. So now I can see, if I'm comparing this number and this number. So object 2 had a much higher charge. It was moving faster, but it wasn't moving perpendicular to the magnetic field. It was moving at a 55-degree angle to that magnetic field. And we see that had a bigger effect on the magnetic force than the charge of the velocity. In this case, if we had raised the charge even more for object 2 or raised the velocity even more, we probably could have seen these things equal out, or object 2 become more. Really though, it's just the angle to that magnetic field does have a huge effect on the magnitude of the magnetic force. That's really the big takeaway from this question. And keep in mind that force that's exerted is perpendicular to the magnetic field. Yeah, but we're going to go through that next time. Good luck with the practice problems.